Hello again, and welcome to Advanced Physics for High School Students. This is Lesson 16, and it is entitled Gravitational Theory. In this lesson, we'll write the equation for Newton's law of universal gravitation, solving some numerical problems at the end of the lesson. But first, we'll tell the story of how the world came to embrace these ideas. We'll meet some of the important people who advanced them. It would not be an exaggeration to say that today's topic, gravitational theory, lies at the heart of the scientific revolution. In unraveling the puzzle behind the motions of planets in the night sky, what was once mystical in ancient historical times became understandable in modern times to anyone willing to accept the physical arguments and to do the math. Your text does a pretty decent job in summarizing that topic, and in this introduction I'll add a few juicy tidbits. Newton's theory of universal gravitation, coupled with his three laws of motion, form the foundation of a mechanical universe operating in a predictable way. It was in this realm, for searching for an explanation to planetary motion, that physics as a science was born. So let's spend a few minutes tracing some of these threads. For us, the story begins with Aristotle in ancient Greece. Aristotle argued that the Earth must be the center of the universe, something that we have come to call a geocentric point of view. Geo meaning Earth and centric meaning center. A geocentric universe places the Earth at the center with all other heavenly bodies orbiting the Earth in perfect circular paths. Why circular? Well, of course, circles are perfect geometrical patterns according to Aristotle, and objects in the celestial realm are perfect. In Aristotle's natural philosophy, the physical laws governing the perfect celestial realm are different from those governing the imperfect terrestrial realm here below on Earth. Since the celestial must be perfect, then objects in the celestial realm are immutable. This means that whatever happens in the heavens does not change over time. The heavens are fixed. One reason people were so interested in understanding the heavens was because they thought their lives were governed by things that happened in the heavens. It was thought at this time that the positions of heavenly objects at certain points in history could direct events here on Earth. And so casting horoscopes was a respected profession. And so someone who understood how the planets moved through the sky were thought to be able to tell you the future. Of course, today you can read your horoscope in the newspaper, and that pseudoscience is referred to as astrology, and that is not to be confused with the serious science of astronomy. Because Aristotle's ideas were so very highly respected, they influenced people's thinking for centuries, and no one thought to challenge his point of view. It wasn't until the dawn of the scientific revolution at the beginning of the Renaissance, when people made measurements that contradicted Aristotle's descriptions, that part of his natural philosophy began to lose favor. The next in our historical cast of characters is Claudius Ptolemaeus. In English, we call him Ptolemy, a Roman citizen of Greek origin living in Alexandria, Egypt, in the early Christian era. Ptolemy's great contribution was the writing of the Almagest. This was a textbook of mathematical astronomy, explaining geometric models of the planets based on combinations of circles, which could be used to predict the motion of celestial objects. Ptolemy presented astronomical models in convenient tables, which could be used to compute the future or past positions of the planets. The Almagest also contains a star catalog listing 48 constellations. Today we recognize 88. Throughout the Middle Ages, the Almagest was spoken of as the authoritative text on astronomy. It was lost to Western Europe by the 9th century A.D., but was preserved, like most of classical Greek science, in Arabic manuscripts, hence the familiar name Almagest by which we know it today. Ptolemy's model, like those of his predecessors, was geocentric and was almost universally accepted until the appearance of simpler heliocentric models during the scientific revolution. Ptolemy's tables were used for centuries to predict the planet's motions, but as time went on, they became less and less reliable. Clearly, something was wrong with Ptolemy's ideas. By the time of the Renaissance, Nicholas Copernicus from Poland formulated a heliocentric model of the universe, placing the sun and not the earth at the center of the solar system. helio meaning sun, and centric meaning centered. The publication of Copernicus's book on the revolutions of the celestial spheres just before his death is considered a major event in the history of science, beginning what has come to be called the Copernican revolution, contributing importantly to the ensuing scientific revolution. Legend has it that Copernicus purposely waited to publish his strange ideas until late in his life, and he received a copy of the printed text on his deathbed. He died a peaceful death and did not suffer in life the upheavals that his ideas had initiated. Next comes the man with the golden nose, Denmark's Tycho Brahe, who is known for his accurate and comprehensive astronomical and planetary observations. Tycho lost his nose at a wedding dance in a sword duel over the legitimacy of a mathematical formula. Chemical analysis done in modern times of a small bone sample of his nose revealed it to be made of brass. Tycho served various kings in various countries during various parts of his life, and those kings financed his astronomical researches, establishing what we would call today research centers. In 1572, Tycho observed a supernova that lacked the expected parallax in Aristotelian sublunar phenomenon, and so he refuted the ancient belief in an unchanging celestial realm. Using similar methods, he showed the comets also were not atmospheric phenomena, as had been previously thought, and he completely gave up on the Aristotelian idea of celestial immutability. Over the course of decades, Tycho observed and recorded many carefully measured positions of planets and stars. These were in the days before telescopes, and he commissioned and built very large quadrants and sextants, working with a staff of people who stayed up all night long, observing and recording the passages of many objects in the night sky, recording the time at which those things reached their zenith, earning Tycho the reputation of the world's greatest naked-eye astronomer. In the last part of his life, he was assisted by Johannes Kepler, who would use Tycho's data for his own ends. According to Brahe's own epitaph, he lived like a sage and died like a fool. Tycho's death resulted from a kidney ailment after attending a banquet in Prague, refusing to leave the banquet table to relieve himself because it would have been a breach of etiquette. He died 11 days later. Tycho's empirical observations, which set new standards for precise and objective measurements, provided an essential foundation on which the scientific revolution was built. Tycho's young assistant, German Johannes Kepler, was the next figure in the scientific revolution, known for his 3 laws of planetary motion. A brilliant mathematician, Kepler cast excellent horoscopes, and this kept him employed for most of his life. Kepler recognized Tycho's data as an invaluable set of numbers on which to build a physical model of the solar system. Kepler's first law, known as the law of ellipses, states that planets follow elliptical orbits instead of circular ones. Previously, astronomers had assumed circular orbits, but Kepler based his first law on Tycho's measurements of the planet Mars's positions over 25 years. It turns out that Mars has the most elliptical orbit in our solar system. All the planets follow elliptical orbits, but the orbits are very nearly circular, and Tycho's observations were just precise enough to give Kepler the data he needed to support his first law. Kepler placed the sun at one of the foci of the ellipse. You might say that Kepler was lucky to have discovered the first law at all. Kepler's second law, the law of equal areas, says that as a planet orbits the sun, a line drawn between the sun and the planet would sweep out equal areas in equal times. This means that as a planet gets closer to the sun in its elliptical orbit, the planet speeds up, whereas when the planet moves farther away, it slows down. This happens in such a way that the area swept out by a radius vector over a period of equal amounts of times, you can take any time you want, several days, or a few seconds, or weeks, it would be the same area for both these planetary positions. Kepler's third law, the law of harmony, says that the ratio of the square of the semi-major axis of the planet's orbit to the cube of its period is a constant for all the planets. Kepler published this last law in one of his most famous books entitled The Harmony of the World, and is based on these 3 laws that Kepler's reputation lies. connecting for the first time the heretofore separate fields of astronomy and natural philosophy. At a later time, natural philosophy came to be known as physics. Isaac Newton will derive Kepler's 3 laws of planetary motion from his own laws of motion and his theory of gravitation. And it will be this triumph of agreement between Newton's theory and experiment, basically the experiment based on the numbers that Brahe measured over time, that gave the scientific revolution its grand influence among intellectuals. But now we're getting a little ahead of our story. A contemporary with Kepler was Italian Galileo Galilei, a jack of many trades, brilliant scientist, original thinker, and reputed troublemaker in the Roman Catholic Church. Galileo is once reputed to have said, "Philosophy is written in this grand book, I mean the universe, which stands continually open to our gaze. But the book cannot be read and understood unless one first learns to comprehend the language and to read the alphabet in which it is composed. It is written in the language of mathematics, and its characters are triangles, circles, and other geometric figures, without which it is humanly impossible to understand a single word of it. Without these, one wanders about in a dark labyrinth." One of Galileo's great contributions were his observations made using the telescope. While Galileo didn't invent the telescope, he did improve it significantly, and then turned the telescope to the sky to make many important observations, including the phases of the planet Venus, finding the 4 largest moons of Jupiter, discovering the rough surface of the moon, and sunspots. He even first observed the rings of Saturn. He wrote down his observations, embracing a heliocentric Copernican theory. Another of Galileo's great contributions was his refusal to accept the authority accorded to previous writers, such as Aristotle, as the basis on which to accept any physical theory. In another place he wrote this: "It appears to me that they who, in proof of any assertion, rely simply on the weight of authority, without adducing any arguments in support of it, act very absurdly. I, on the contrary, wish to be allowed freely to question and freely to answer you without any sort of adulation, as well becomes those who are in search of the truth." Instead of trusting Ptolemy's geocentric ideas, Galileo pointed to the moons orbiting the planet Jupiter, which he could plainly see through his telescope, and eagerly showed it to others. Instead of accepting Aristotle's pronouncements on, say, the rate at which different objects fell, Galileo measured the rate of fall. At the end of his life, under house arrest because of his confrontation with the Church, Galileo wrote this: "Aristotle says that a 100-pound ball, falling from a height of 100 brachia, which are arms' lengths, hits the ground before a 1-pound ball has fallen 1 brachia. I say they arrive at the same time. You find, on making the test, that the larger ball beats the smaller one by 1 or 2 inches. Now, behind those 2 inches, you want to hide Aristotle's 99 brachia, and, speaking only of my tiny error, remain silent about his enormous mistake." Not only did Galileo observe the heavens, he experimented on earth. In one of his famous studies, he rolled balls down ramps, watching how far they rolled up adjacent ramps, inclining the adjacent subsequent ramps at smaller and smaller angles, and finding that the balls tended to seek the same height from which they were released. From these observations, Galileo developed the concept of inertia, or the tendency of an object to maintain its motion. Galileo was able to conceptualize ideal situations in which friction behaved just as any other force. His ability to idealize the motion allowed him to advance many seminal ideas. On this topic of idealization, he wrote this: "Just as an accountant who wants his calculations to deal with sugar, silk, and wool must discount the boxes, bales, and other packings, so the mathematical scientist, when he wants to recognize in the concrete the effects he has proven in the abstract, must deduct any material hindrances, such as friction or air resistance. And if he is able to do that, I assure you that things are in no less agreement than are arithmetic computations. The trouble lies, then, not in the abstractness or concreteness, but with the accountant who does not know how to balance his books." Galileo played a major role in the scientific revolution, championing the Copernican theory, laying before the world a series of observations and logical arguments that was difficult to refute. His support of heliocentrism during his lifetime, when most of the rest of the world subscribed to geocentrism, put him in conflict with the powers of his day. In 1615, he was investigated by the Roman Inquisition and was instructed to cease his teachings. Later on, Galileo wrote a controversial work entitled A Dialogue Concerning the Two Chief World Systems, which appeared to attack the Pope. One system was the geocentric model, the other system was the heliocentric model. He was tried by the Inquisition. He was found vehemently suspect of heresy and forced to recant, spending the rest of his life under house arrest. Toward the end of his life, he wrote a work entitled Two New Sciences on the Fields of Kinematics and the Strength of Materials. Galileo died in the same year that Isaac Newton was born. Christmas Day, 1642, Newton entered the world, and he drew together all the threads of these previous ideas, producing a work in Latin known as Principia, in English, the Mathematical Principles of Natural Philosophy. In Principia, Newton laid out his three laws of motion. The first law, called the law of inertia. His second law, the law of force, mass, and acceleration, which, by the way, is the most mathematical of the three. And the third law, known as the law of action and reaction. Combining these three with his law of universal gravitation, Newton laid the foundation of a mechanical universe in which the principles governing the motions of objects here on Earth also govern the motions of objects in the sky, uniting the terrestrial and the celestial realms in a most revolutionary way. No longer are objects in the night sky moving in mysterious ways. With Newton's ideas, one can predict what's going on and what's likely to happen, and this knowledge of the motions of heavenly objects is one of the crowning achievements of the scientific revolution. It is Newton's law of universal gravitation that occupies our present attention. And so, with this historical introduction out of the way, let's turn to examining the law of universal gravitation in some detail.